Welcome everyone to GOF 2.0 virtual trial in Klagenfurt, Austria. Before going into the trial, we will provide from GOF 2.0 consortium a brief introduction to the project and to the trial as well. I am Maria Tamm. I'm from Estonian Air Navigation Services, a project manager for GOF 2.0. And GOF 2.0 integrated urban airspace is one of several very large demonstration projects in Europe funded by SESAR Joint Undertaking under Horizon 2020 program. And the project will safely and securely demonstrate the operational validity of serving UAS, eVTOL and manned operations in unified dense urban airspace, and doing it by using current ATM and use-based services and systems. And the idea of these demonstrations is to focus on validating the GOF 2.0 architecture for highly automated operations in dense airspace, including precision weather and telecom networks. So we have an international consortium of 15 members with excellent expertise to do it. We have 3 ANSPs from Estonia, Finland and Poland. We have a robots expert leading demonstrations, consulting companies on unmanned aviation. We have several companies providing various UTM solutions and technical infrastructure. We have Frequentis, Drone Radar, Aviamaps, and also Airbus Urban Mobility. In addition, the consortium members include Unmanned Life, enabling AI for autonomous solutions, mobile network data exchange by Demeter, weather information provision from Vaisala, and of course drone operators Drei Systems, Gafatech, and Poznan Supercomputing and Networking Center, who is also an IT infrastructure provider in the consortium, and in addition EHang, an autonomous aerial vehicle technology platform company. Next slide, Tanel. So the logic of GOF 2 project set up for demonstrations and trials, we have identified altogether 11 operational scenarios which represent the majority of urban air mobility operations. And as you can see on the slides, these vary from various surveillance flights to delivery operations, but also included eVTOL and helicopter flights. And there are 3 main trials, and the idea of these trials is to demonstrate the different airspace interaction types. Trial 1 focuses on mixed airspace in CTR, and as most large cities reside within CTR airspace, we need to work towards separation to enable intra-urban urban air mobility operations. Trial 2 is about entering and leaving airspaces and CTR, and this is related to peri-urban UAM operations linking together suburbs and city centers, and this will require smooth procedures for entering and leaving different airspace types. The third trial is cross-border flights in use-space, which focuses on interurban and or intercity UAM operations to connect cities through air. And And this trial will demonstrate then how interurban UAM, eVTOL, and unmanned operations can operate end-to-end in new space. Altogether, the trials are planned in two waves. The wave one for 2022 has been intended as an initial live test for the functionality of the interconnectivity of all systems used in the project. And we have been focusing on collecting initial performance and operational data for more advanced scenarios in wave two. As in wave two, we will test we take a more dynamic approach to airspace management and deconfliction services, and also include more elements of surprise to really test the actors and systems to operate in an integrated airspace. And there is also a fourth trial. It is a roadshow trial, and this is to really demonstrate the scalability of the GOF2 architecture by operating a certain subset of these scenarios in 3 countries of selected advisory board members, namely in Latvia, Denmark, and Sweden. So far, the work has been done leading up to the advanced flight trials, which are dependent on building a more scalable and interoperable use-based architecture. And with this, I give over to Thomas Lutz from Frequentis, lead of technical integration in the project, to provide a more overview of the technical work done so far.
Thank you, Maria. Thank you for putting me on stage. Let's assume that GOF2 is all about technical integration, and let's remember the last half year, well, 10 months actually, since the project started in January. Some probably will remember the times as a bit indicated by this picture. Putting gears together, putting systems together, forming a system of systems, focusing a lot, at least in work package 2, on technical integration. One might think GOF2 is all about technical integration, but let's look at that a bit in the next slides. Next slide, please. Exactly. Who is integrating? Let's talk about the systems first, the products that we have in there. What you see here is the average architecture drawing depicting elements, stakeholder systems that are part of the UTM use-based environment. Let me highlight a few. Please click once so that we get the box. Let me highlight a few. Our focus is on drone operators, clearly. This is what it is all about, enabling drones to fly, enabling operators to grow their operations, to grow their business, ultimately. To do so, there's service providers, several of them. There's, of course, air navigation service providers. In use-based, there's a common information service provider. This is the CIS that you can see on the right side in the bullet-pointed list. There's use-based service providers, and in GOF, and they will play an important role today, there's supplemental service providers as well. All the service providers, they technically talk to each other, and this is what we've done in the first months. Look at the systems, look at the use cases that have been introduced by Maria before, discuss what we need to make these use cases happen, to make ultimately the drone flights happen, and which information respective systems and services would need to do so. Next slide, please. And that's been a funny journey, less technically, because I think it's, first of all, more fun and easier to explain. Use-based UTM, to most of us, especially in the beginning, looked like one of these famous big elephants that you need to break down. And depending on your respective component on your system, that elephant might look different. Some might think that this is a hose, as it's on the drawing here. Others might consider it being a tree. It very much depends on that part of the big system of systems that you see and that you're focused on. In other words, needs and services and products of a drone operator are different from those of a service provider. And to make them work together, you require common understanding. Click once, please. And that common understanding is very easy to achieve if you focus on the infamous W's. You need to get the stakeholders agree on what are we actually doing, use cases. Why are we doing this? Well, to grow business, to make some things more efficient, to do parts of aviation in a different, more future-proof, more green way. Where do we do it? Specific places is used as a bubble. Is it a corridor? Is it more? Let's figure that out. Who does it and when do we do it? And if you discuss those questions, you start to uncover that elephant that the big system is, and you start to understand that even though it looks like a tree for you personally, it might be a wall or a rope for somebody else. And you start to shape out how this elephant looks like. And that way, you eventually figure out on how to do things. Next slide, please. And this figuring out, you need to document. You need something in writing to make people and systems understand. And this is a bit more technical than before, but still on the left side, you see system A. That might be a system that says, for me, the elephant looks like a tree. On the right side, you have system B. Somebody might say, this elephant looks like a rope. When they talk, focusing on the W's, sooner or later they reach common understanding, and then they write down things like an information model. How does this rope look like? How does this tree look like? Or in aviation terms, how does a position look like? How does a flight plan look like? For both systems, you map those models, interfaces, and the behavior of this interface that you connect to let's say, least common denominator, and you write it down in the so-called service specification. This is what we've done in the first months of the project, to have something to discuss, something that we can use as a guide to integrate systems. And as soon as you've written that down, and as soon as everybody keeps in mind that behind the tree and behind the rope, there's an elephant, things start to get easier. Next one. Last content slide, promised. And looking back a bit, you could compare it not only to an elephant, but you could compare integration in GOF2 and probably integration in most of the IT systems, a bit like the process of building a house. First thing, you have to make sure that everybody, and really everybody, has the same view on what you're building. The builder, the plumber, you, and eventually your family that is going to live in that house and might have a different view on which room should have which size and how that house should look like. You need something to communicate. Common playground, a common frame that defines how things will work out, a plan. You need to coordinate your partners. You need to coordinate the plumber, the builder, putting up the house, and finally putting it together to something where you can live in. And you better start with the basement. So don't take the roof forward. Take it slow. Start with those things that are used as foundation afterwards. And this is what we've done in the last half year. We've integrated, looking at telemetry data, who is where, looking at operation plans, flight plans, declaration of intent, who will be where and when. We looked at operational messages, communication between operators and the airspace manager, telling people that, for example, they are outside of the declared intent, that they have a non-conformant operation. We looked at no drone zones, informing people that the airspace is closed, and we will see a bit more today with supplemental services. Next one, last one. And when you do that and talk to each other, you finally find out it's a bit on technical integration, but it's more about operational integration, making systems work together, making the partners work together, achieving something. In the end, it might look like a technical integration project, but actually it's more about building trust between all stakeholders. Air traffic control, airspace managers, drone operators, system providers, manufacturers. You can look at the partners list. It's really a diverse ecosystem, and it only works if people work together. And this working together, you see very much in the operational integration. And so I hand over now to Jonas talking about the actual trials.
Thank you, Tom. So my name is Jonas Schärnberg from Robots Experts. We are overseeing the planning of the trials, and we have Tanel Järvet from Kafatec being the trial coordinator for this specific trial. But let me introduce on 2 slides what we will see today. You see on the left top side a zoom in of the Klagenfurt airport area. And on the right-hand side bottom, you see a larger scale map where we have some missions going further away. Today, everything is simulated. In the spring of next year, we hope to come back and do some of these flights for real. In yellow, you see Unmanned Life will be conducting drone deliveries from the airport area to the shore of the lake in Klagenfurt. Triad, meanwhile, will be doing surveillance over the airport area, whilst Kafatek in blue is doing mapping flights at low altitude to get a 2D map orthophotogrammetry of the area. It so happens that Unmanned Life is delivering some delicious food items that was just flown in to Klagenfurt Airport to all of the VIP guests who are now being transported by EHang's electrical VTOL air taxi also to the same location of the seashore. The neighbor, who is a little bit south, got so green out of envy that he got a heart attack, and we need a HEMS flight to fly from the helicopter pad at the Klagenfurt airport to the seashore and rescue a vital life. And Dimitar will next, after my 2 slides, talk a little bit about mobile network connectivity. For long-range flights, to be connected to the drone at all times is vital, and they are illustrated in light blue to the left. When we look at the systems later, you will recognize these geographies. Next slide, please. So we have several parallel flights with drone mapping flights, automated parcel delivery, surveillance, HEMS, eVTOL, etc. in different sprints. The trial, the T0 is planned for 9 minutes from now at past, and then the trial will go on for about 47 minutes, after which we will conclude for questions and answers. When we are flying, we will pass the mic around to the different consortium members, and you will get commentary and different aspects of the whole missions. With that, I hand over to Thomas Neubauer from Dimitar to take it from here. Thank you.
Thank you very much, Jonas. So my name is Thomas Neubauer. I'm representing a solution called Airborne RF, and it is my pleasure to talk about how GOF2 takes actually connectivity into account, which is one of the objectives here in the trials today. To safely operate unmanned aerial vehicles at scale in an integrated airspace, a reliable and scalable digital communication is a must-have. This is true for safety-critical and mission-critical communication, and I will explain that further down the road. The important point, however, is if you don't know where connectivity in airspace provides a minimum performance, you practically don't know where you can communicate or not. And that adds a safety risk that is just not acceptable in aviation. Therefore, what we see here, the system of systems architecture in GOF2 takes that data into account. Supplemental service providers, as we see at the bottom, such as mobile network operators, not only provide reliable and scalable connectivity for the lower airspace, they also have all of the information available to understand and communicate where communication in the airspace is possible for safe drone operation. And in order to exchange such data, there have been 2 main challenges. First of all, historically, there was no interface between the telecom industry and the various players on the aviation side. And as you can see here in this picture, the interfaces to the various players on the multiple aviation stakeholders are actually quite a few in number. Secondly, cellular operators are actually very careful about the exchange of this highly classified and confidential information, which essentially goes to the core of the network. Next slide, please. This is why the global representatives of the telecom industry, GSMA, and the Global UTM Association have actually joined forces to come up with a universal standard for such interfaces which have been approved earlier this year in the architecture that you see here. In today's GOF2 trial and presentation, we will see for the first time the operational end-to-end live implementation of that interface in a real-world deployment. If you click once, you see that the UTM system on the right-hand side, if you just press once, yeah, exactly. The one that is used today is Frequentis. And what we are to connect with is, if you click another time, will be the live network of Drei, a leading 4G and 5G mobile network operator in Austria. The solution facilitating that would be the last click, based on these global standards, is the solution called Airborne RF that I'm representing. So if you click once on that, that would be great. I will explain the details of the actual implementation and what it does later on. So what you will see is how a UTM system is, via Airborne RF, requesting information about the live airspace connectivity information from the actual cellular network as is at that point in time. The automated processing and data exchange is then providing the results back to the UTM system so that it can make a more holistic and better decision for the flight planning and the flight operation. That's from my side. Details on that come later.
Okay, thank you, Thomas. Thank you, colleagues, dear guests. My name is Sven Jürgensson, and on behalf of Estonian drone manufacturer Drei Systems, I briefly explain our expectations and reasons to be part of the project. So on this slide, you can see our aircraft that is doing most of the flights in GOF project for us. And now about the expectation. Although Drei began in the field of defense and security, our products are also increasingly used in other areas, such as search, rescue, environmental, and so on. So these missions are often conducted in public airspace. Our desire is to contribute to the development of safe and efficient use of urban airspace, which is also the main reason for us to participate in the GOF 2.0 project. Thank you, and handing over to Tanel.
Thank you very much, Sven. And let's continue with drone operator manufacturer expectation. My name is Tanel Järvet from Cavotec, and Cavotec is an Estonian robotics company, and we are developing autonomous and teleoperated cellular drones for network quality of service measurements and for logistics. And regarding GOF 2.0 project, our main expectation is to use automatic PVLOS drone flights from 2023. And we fully understand that in order to use the airspace, we need to integrate our ground control and command and control systems to UTM systems to share our flight schedules, flight plans, and share drone locations and telemetry with national air navigation service providers. And the GOF 2.0 project helps us to integrate our GAFA ground control system with 3 UTM systems, as mentioned before, Frequentis, Panza, UTM, and Aviamaps, and also with national air navigation service providers. And let's continue here with the general overview, what we are expecting from GOF 2.0 project. You can see on the first lower level ground control systems of drone operator companies, Cavotec, Drei System, EHang, and one simulator provided by Unmanned Life. On the second level, you can see Panzer UTM, drone radar and frequencies and aviamaps UTM systems. And as Thomas Neubauer introduced, the Timetor as additional service provider. And all these systems integrated with our navigation service provider. We conducted such 3-level test in Estonia, in Tartu and Tallinn, in Helsinki, and in Kakoleva in Poland. And now today we are conducting virtual trial virtually in Austria, in Klagenfurt. And let's continue with mission timing. Now it's 1:30, it's time 0. And we will have 8 different flights, and starting with drone mapping flight from Kafatec. And then we will continue with automated parcel delivery, drone surveillance, HEMS helicopter, medical helicopter flight, automated parcel delivery, and drone delivery using mobile network coverage. But let's continue with screen sharing, and I'm starting to share CAFA ground control system screen. And you can see how we have planned the 3D mapping flight to map Klagenfurt Airport. And it's a UGGS ground control system, added some core functions to integrate our ground control systems to the UTM provider frequency system. I will start sharing also the frequencies smart system to showing that we have uploaded the flight plan, pending plans you can see, and one approved plan, CAFA flight plan. And now as the flight plan is approved, you can see on the screen Klagenfurt Airport, the 3D mapping flight. And as the plan is approved, then we can use for our drone the arm, then auto mode, and we can start 3D mapping flight. You can see that Kafatec drone just climbing, the takeoff, and we can check on the frequencies UTM system that our drone is visible. It's a foundation and absolute condition for using integrated airspace. You can see drone flying on the Klagenfurt Airport. I will start sharing here the screen, and you can see the same drone, Kafatec drone. It's altitude 110 feet and flying on the same route at the same time. I will start sharing a short video about how Kafatec conducted our medicine parcel delivery flight in Tallinn. We conducted paracetamol delivery flight in north of part of Tallinn, where we delivered one paracetamol to our destination. And let's see the destination and flight over the some 100 meters. Then in Tallinn, we had about 60 visitors, and we conducted field trials with our partners, GOF2 consortium partners. And finally, we got all trials successfully, as mentioned, in Estonia, in Finland, in Poland. Here is one group photo from Tallinn. And hope we can see our visitors also today during the group photo time at the end of our virtual trial. But let's continue with ground control system. You can see the drone flying. And I would like to ask PANSA UTM team, Piotr, to start sharing your screen and showing how PANSA UTM showing unmanned life simulated drone flight, because we are using also the simulator provided by Unmanned Life. Please, Piotr.
Yes, hello. So this is Paweł Korzec speaking from Drone Radar. We are together today with PANSA UTM. So this is the view of the UTM system, which you can actually meet on every tower, civil and military in Poland, and gives you the situational awareness of the traffic. So when we make a zoom in, you will see all flight plans forwarded through the smart system to the PANSA UTM systems, together with the telemetry integrated. So when you press the button on the line, you will see also the parameters. You can approve or reject the flight plan. You can also activate the flight plan. You have telemetry details with information about current status of the flight and the current status of the telemetry. So this is how it works. It shows basically the full integration with no delays. This is very stable connection between the CIS systems shown via the USSPs. Thank you.
Thank you very much, Piotr. And I would like to share again our mission timeline, and then we can start the next step. But first, our timeline. We are conducting currently the drone mapping flight, and the second flight is Unmanned Life, automated parcel delivery, simulated flight. And next, we are preparing for drone surveillance flight, ordered by, on simulated way, ordered by police to providing the bird view at altitude 120 meters. And I would like to ask Sven or Ivan from Drei to take over the screen and showing Drei flight mission, please.
Good afternoon. This is Ivan from Drei. Now you can see on this screen it's the Drei proprietary ground control software, and we have prepared a mission for airport surveillance. And as of current operational authorization, we are capable of flying up to 120 meters above ground level and up to 1 kilometer distance from piloting command. Drei has a direct integration of the software to the smart sys. Currently, we have only integrated the telemetry sending. It is as easy as pushing a button, and the telemetry of the drone will be automatically transferred to smart sys. The flight plans are created manually, and alerts and geo zones we see on either smart sys or any other system mentioned before. We are working on integrating the other functions for the next phase. So now I would like to hand over the screen to Aviamaps and prepare for the virtual takeoff of EOS VTOL aircraft.
Thank you very much, Ivan. And Juha or Marwan, please.
Yes, thank you very much. So we are Aviamaps, and we are modernizing manned and unmanned aviation with unique real-time aviation map platform so that both aviators and drone operators don't need to guess where to fly and where not, but to know that exactly. And I could quickly show that we are currently operating in Finland, and here's the real-time airspace is of Finland. So we have the AUP, UUP data here. We have all the supplements and also NOTAMs, and also drone pilots can announce their flights, so we can see a few drone pilots here operating. But what comes to GOF2, so here's our integration with the SmartSys system as well. So currently we're seeing the Threod drone here flying, and there's the EHang drone, and we have the operation plan here showing. So yes, here's our integration, and forget to mention that we are adding more countries to our service as well. So yeah, thank you.
Thank you very much, Juha from Aviamaps. Now we have shown 3 systems. First Frequentis and Pansa UTM, and then Aviamap systems. And let's continue. As you can see, we are waiting unexpected HEMS helicopter, medevac helicopter takeoff need from Klagenfurt Airport, and I will give over to Thomas Lutz from Frequentis to showcasing this flight. Please, Thomas, or Gregor.
We'll split the work, so I will talk and Gregor will share. Thomas Lutz again. What you see is SmartSys, the front end to our UTM system, operational as well. And let me underline this, all the components that you've seen so far, they are all used in real life operations as well, be it UTM system, be it ground control station, and apart from this being a simulated trial, drones, of course, used operation as well. So this is cutting edge. We've added some features that will be in production soon, not yet, but everything is based on real systems connected to one big system of systems, just by looking at interfaces and by agreeing how these different objects look like. What you currently see is, based on a 5 minutes notification, HEMS flight will be taking place from Klagenfurt Airport to the east side of a lake near Klagenfurt, Wörthersee. And you can either restrict the full AR or, as you've seen here, you indicate which geometry, you indicate which time, and you just create it by clicking save. The end is set, the so-called no drone zone is created. And now a few things happened. The no drone zone is intersecting both in time and space with known flight plans in the system. And every flight plan that is intersecting is then processed by the systems, and eventually a notification, an alert is sent to the drone operator, letting the drone operator know, as you can see on the right side, that the drone should be landed immediately and that landing should be confirmed so that we have a clear state and can clear the airspace for the HEMS helicopter. A few things will happen now. Drones will move away or will climb to get out of the so-called no drone zone. Maybe handing over a bit to Tanel and to Friot to explain what the drones are actually doing.
Yes, thank you very much, Thomas, and I will start sharing the current situation with the timeline. As you can see, HEMS helicopter need to send out the alert 5 minutes before the actual flight. And the actual flight is planned 017. And after that, we should ensure the free airspace for HEMS helicopter. And our plan is currently regarding Drei to provide possibility for Drei plane to climb up to the higher. And then we can continue with Kafatek and other smaller drones, simulated drones, to immediately land before the takeoff time of unexpected HEMS helicopter. I would like to give over to Jonas, and then after that I can share our screen. Maybe Jonas can explain a little bit how the plan, how actually working the workflow between drone operators and HEMS helicopters. Please, Jonas.
Thank you, Tanel. I will start sharing my screen here in a second. So now we are, hopefully, you're all seeing a screenshot of the drone radar application with the alerts for the different operation plans which you have on board. You can see different targets here in white, which means that they are reported via telemetry. In some of the trials, we've also had ADS-B signals automatically received in the system, and then you will find red diamonds showcasing that you can really trace all sorts of targets in the system, and you see them moving. If you click to SmartSys, and we have the no drone zone here, you will actually see the same data, a little bit different symbols, little different metadata associated to it, you know, altitudes, etc., and operation plans. But by and large, you see the same operational picture here. We are working on some things, added functionality all the time with some elements such as the no drone zone. So for instance, in Avia maps, the no drone zone is not yet implemented, but this is something we will have for wave 2. And you can again look at the operational plans and see the same picture. The point here is that in order for aviation to be safe, every aviator needs to base their decision making on common information. And common information, the most crucial ones are where are our aircraft situated and what are their intent. Then we are adding the other functions on top. So I think just briefly with that one, handing over the mic to the next speaker. Thank you.
Thank you very much, Jonas, and let's continue with our next flight as planned. I will start sharing again the time schedule that everybody can see. We continue with unexpected HEMS flight, and let's conduct this on the simulated way. And Thomas from Frequentis, maybe you can share your screen and show how the HEMS helicopters flying on the simulated way.
Gregor Nimsten. HEMS helicopter ready for takeoff, and HEMS helicopter taking it away. So you can see the HEMS flight going through. Just in case you wonder why it's a drone icon, can be a drone. Passenger carrying drones, probably very likely for sure are the future. So in that case, it's classified as drone, as it's an unpiloted one. Climbing high, going fast, approaching the eastern part of Wörthersee. While it is flying, you can see we've got still some room to go. Maybe a bit on the background of the applications and on flight plans and telemetry and all the buttons and colors that you see here. So in general, the concept is that initially you declare your intent. You send a request, a pending operation plan, and based on other operation plans that already have been requested, based on no drone zones, based on so-called geo zones, areas where drones are not allowed to fly, the systems can answer and tell you, go a few minutes later, earlier, shift your flight plan a bit, or simply say, yes, you're good to go, or no, you're not good to go. Once this strategic decision is taken that the flight is good to go, it moves from pending to approved. This can be done automatically, as I quickly sketched out before, or it can be done manually for special areas, for example, around towers or over critical infrastructure. There can be overrides or supervision by human controllers. Once the flight is taking off, once the drone is armed and in the air, the flight moves from approved to active. This is the green ones, indicating that within this area, there is already a drone. In real-world nominal operations, so if everything goes according to plan, you would rather look at these flight plans, at the operation plans, at the volumes, and not look at the respective telemetry. Telemetry is more for going in detail for specific flights, as it quickly gets a lot of information on one screen for people handling the system. So the systems are built to focus on specific tasks and specific situations, and would hide drones that are conformant within their declared volume, both space and time. They would hide them, not show them, because actually there's no action to take. Everything works according to plan. The systems can deal with it, and there is no need to interfere. The HAMS is now approaching the lake, going a bit north of this peninsula where it's actually going to land. Let's assume we have wind from the south, and approaching. Going on with the things that you see in the screen, same concept in all the applications that we have in here. You have pending plans, approved plans, active plans. Upcoming plans is for future flights. I hope you can read it, but this is like for flights that are for 60 minutes plus, in the meaning of starting in 1 hour or in 1 day or 2 days. I think it's worth mentioning most of these flights are quite short notice, so to say. So requests come in within minutes, 10 minutes, 15 minutes. Requests are approved within minutes to make it easy and super efficient to fly. You have an overview on active drones. This shows all telemetry. And the last two ones, this is the no drone zones, where you can either import data, connect to external systems like geozones provided by, for example, authority, or no drone zones set up by public safety or by other authorities that are authorized to do so. Alert messages show a sample of everything that has been sent out to other systems and operators. With some additional information, you can change the flight. You can see if the operator answered the alert. And actually, this is what you need to do in tactical operation. So all the systems are focused very much on efficient way of working with them. So the HAMS helicopter has landed. On the map, we see 0 feet, so it's on the ground. HAMS helicopter on the ground means we can cancel now the no drone zone and continue with the operations of the trial. Over to the next speaker.
Yes, thank you very much, Thomas. And let's continue with our next flight, EHANG eVTOL intra-urban flight. And Juhank, floor is yours, please. or maybe yes, Johan.
First,
yes.
we need the approval of the flight plan from the Airspace service provider.
Yes. And you can start sharing your screen if the flight plan is approved, and then let's continue with EHang eVTOL flight.
I would share our screen. Hello, everybody. This is Yuhang speaking from EHang. This is our flight plan. We have developed the EHang 216. It is the first passenger-grade autonomous eVTOL in the world. And for the virtual trial in Klagenfurt, we are using our EHang 216 to conduct an autonomous BVLOS flight. The journey is about 6.5 kilometers, representing a passenger transportation use case from the helipad near Klagenfurt airfield to the dock at the lakeside. It will take around 7 minutes. Here is a video clip illustrating the entire flight from taking off to landing. Now we are on the way flying to the lakeside. Thanks a lot.
Thank you very much, Johan. And let's continue with next mission. As you can see on the time schedule now, we are preparing for our connectivity, cellular connectivity mapping flight and drone using the mobile network coverage data. And over to Dimitar, Thomas Neubauer, and Frequentis Thomas Lutz to share your screen, please.
So here again, sharing screen from Gregor. Quick look here, you see close to the mount pointer, this is EHang flying. And again, mentioning this is a real ground control station, driving a real drone, just that it's not connected. And what you see is a system-to-system integration of the ground control station that would actually be used to fly a real 216. Sending from the ground control station to servers, connecting to the UTM systems and being broadcasted to all connected stakeholders. That being said, the flight that we have planned to deliver using a flight plan based on mobile network coverage is quite a long one. So we will start that right away. This is the long green flight plan that you see on the going over Wörthersee, so over the lake. And I will let the drone take off. And now it's green. Now I can start. Dimitar flight is starting up here, climbing, as most of the other drones first going vertically up and then starting to move. Same concept as before, as you declare intent, you wait for an approval, and once you have the approval, you activate the drone, flight goes to active, and then you can follow it on based on the telemetry data. The actual reason for this demonstration flight is a bit different. So what we've been doing is using supplemental data in flight planning. And to explain that and let you take a breath by listening to a speaker for a bit longer than just 1 minute, I hand over to Thomas Neubauer, who will guide you through the mobile network coverage aspects. Thomas.
Thanks, Tom, for that. As mentioned before, connectivity for drones and UAMs is critical, especially for beyond visual line of sight flights, but generally for integration into the airspace. But before I go into the details of what we see here in the implementation, I would like to add some basics for those not so familiar with the actual topic. And that typically starts with the question, why is connectivity for UAVs so important? Can't they fly fully autonomously? Well, just think about the case where a UAV does not have connectivity to a ground control, a UTM, or an equivalent system. It could not be controlled or commanded in case of an emergency. It could not be provided information only visible to the ground control station, and it may even be perceived as a non-cooperative aircraft, which is clearly the last thing you want to have in such an environment in the airspace, and it is thus a risk that is not acceptable. Also, legally, like in manned aviation, there has to be a pilot in command who is responsible. Without having a pilot physically on the aircraft, it can only be a remote pilot. And for that to work, a reliable connectivity with the ground control station is a must-have. So what you see actually in the deployment here is the following. The UTM system, so the ground control system in this case, as shown by Tom Lutz and Frequentis, has a request regarding the connectivity information for the considered flight corridor. This request is provided to Airborne RF in the background to retrieve the results from the mobile network operator. On the receiving end, in general, live network data is highly classified and confidential information, as I mentioned before, to any mobile network operator worldwide. So in order to make happen what we just described and to bridge this information gap, Airborne RF consists of two components. The first component is to provide this interface to the ground control station, to the UTM system, which is enabling the secure and fully automated real-time exchange of data. The second component of Airborne RF is, as we speak, actually hosted and operated at the live network operational center at Drei, the mobile network operator, in Vienna. And there, this component is having access to all of the relevant data that is needed to compute the connectivity information. Therefore, when we have seen this request, or when we are seeing the request from the UTM system, Airborne RF translates that into to the request for the processing at Drei in Vienna. The processing there takes all the live information of the network into account. And once that is done, the results are sent back here to the UTM system. So in short, by deploying Airborne RF, all of the required information for the UTM can be provided, which clearly adds to the safety case and without any concerns for mobile network operator Drei. So what you see there is we have two paths actually. One is green and one is actually green and interfered by some reddish orange areas. I will explain why that is. But before, I would like to answer another question that typically comes up, which is why cellular? Well, cellular networks are not the only option, but easily the most attractive one. The reason is that mobile networks have not only demonstrated over the last 25 years that they can do reliable communication at scale for billions of connections worldwide, but they also provide the security levels they are widely available, commercially feasible, and they are great when it comes to the so-called swap factor, so size, weight, and power of the actual modem. They can also provide the required bandwidth because in addition to the safety critical information and communication that is needed to conduct a safe drone operation, there's also a need for what is called service critical communication. Just think about a first responder drone that actually has to provide live pictures and video material from an emergency event to the mission control center without having a broadband connection. That's pretty useful. One important aspect is also that cellular networks are working in licensed spectrum, which is particularly important as in many jurisdictions an SLA, so a service level agreement for these connectivity aspects, can only be provided in licensed spectrum. And finally, the upcoming 5G networks, and we are absolutely pleased to have the capability with Drei to actually operate also in 5G networks. They will provide capabilities called network slicing, which are specifically exciting for drones and aerial applications. In simple words, you can make some of the 5G network, a so-called slice, behave like it is a dedicated network for airborne applications. So what you see then here in the UTM as an additional data layer are different colors for the cellular connectivity along the flight corridor. Green means that the requirements for the so-called minimum operational performance standards, MOPS, are met. Red and orange means that they are not met, and thus the risk of having insufficient connectivity or a loss of connectivity is high. This is also a reason, or one of the reasons why we are interested in showing that in this interaction of the various systems is that in the upcoming phases of GOF2, we will not only demonstrate the import and the live consideration for the data, but we will be flying drones live, also via cellular command and control over both 4G and 5G networks, and therefore we have to know where connectivity can be expected and where not. Coming back to the requirements, what actually makes a connectivity good enough? So why is it green and in other places it is red? Well, the global standardization bodies responsible for that, called EuroK and RTCA, are currently defining the various categories for such connectivity by the following item points. One is the availability of the connectivity, the continuity, the latency, as well as the integrity, meaning the reliability of such a communication link. Green here means that these requirements are all met, and as mentioned before, red-orange means they are violated. Reasons for that can be that there is, for example, not good enough signal available, so there's no coverage, but it could be also that there's too much interference. As cellular networks have not been optimized for aerial users so far, a drone will actually have a very different connectivity situation compared to mobile users on the ground, and interference in that context means that a drone can have signal contributions from having visibility to many different cell towers at the operational altitude, which is usually many more than what you see on the ground. It is a bit like when you go to a sports bar and 20 or 30 people are actually watching a football match. You are rarely lacking signal, but because so many people are speaking, you can't hear your neighbor. The same concept applies here for interference in the communication link. Regarding the actual values, the performance thresholds for the respective requirements, this is currently under investigation on a global scale. And with GOF2, as part of the next phases, we will also provide airspace characterization that will help out finding what these thresholds actually are and what makes them good enough. I'm sure there may be some questions on that, as we will in the subsequent trials also get live notifications from the cellular networks to the airspace management systems in case something happens during the course of a flight. As we see, such flights can actually have quite some duration, and those demonstrations will follow in the subsequent trials of GOF2. With that, I hand back to Tom Lutz for further words that you probably want to talk about in this case.
Yes, Thomas, please.
Continuing, looking at the remaining flight time, I think that the key part, repeating the message a few times today, is bringing things together, bringing systems together, bringing information together. Production systems or systems in operations, maybe easier and better to understand. Being airborne, being in the MNO, in the mobile network domain, being in aviation, systems that are around for like a few years in traditional ATM, systems that will be there in 2 or 3 years in UTM and ATM as well. All to reach common understanding and making those drone flights happen in a reasonable way. Looking at time, I think that we can, while we look at the drones completing the flights, already start Q&A sessions using the last, let's say, 20 minutes of this meeting and open the floor for discussion and comments. Maybe we can risk by just saying, raise your hand and we'll try to name you and then speak out. Talk to us, ask us questions.
Thank you very much, Thomas. And thank you very much, all drone operators and UTM colleagues. Let's continue questions and answer sections. And I can see Pavel Montov raised hand. Please, Pavel.
Yes, hello everybody. Thank you very much for very nice and impressive presentation. During the session, I had one question I noted. When the HEMS helicopter was starting, there was this 5 minutes waiting time before takeoff. Is it because other drones were already in the air, or is it something what anyway take some time for HEMS to start to take off?
Yes, thank you, Pavel. Very short answer. We discussed before the trial what would be the actual preparation time, and indeed, even a helicopter needs some time for preparing takeoff. We consider it 5 minutes. Maybe it's a time should be 4 minutes or 6 minutes. It's a fine tuning, but maybe some other colleagues can comment. But anyway, based on the HEMS task, we can alert our drones some minutes before the HEMS helicopter takeoff.
Okay, and then another thing which was not clear for me, what happened to the drones which were removed from this non-fly zone when it disappeared? They continued, or they need to reapply for the new flight permission?
Yes, during the effective time of no-fly zone, the drone operators can apply for exemption, but normally they can see the no-fly zone, temporary no-fly zone, and postpone the mission and waiting until the HEMS helicopter left from Klagenfurt airport, and then drones, smaller drones, then can take off.
They can continue. Okay, thank you very much. Thanks once more. That's all from my side.
Thank you. And I can see Lehoslav raised hand, please.
Nice to be here with you as a guest. Nice to see old friends in a new incarnation, because I come here both from Orange Poland and from the 5G drones project. So very interesting presentation, something which is quite new for me, as I'm a person from the telco world, not from the aviation world. However, Paweł Korzec already taught me a bit, so I recognize the operations that I was described by Paweł. But of course, my interest is mainly focused around the tools for, let's say, integration of the telco world with the aviation world. I mean the RF airborne, which was presented by Thomas Neubauer. Of course, the general idea about of the interface between the aviation and telco domain is quite obvious for me, but it would be very interesting to know, probably not today, but in a dedicated presentation, to see what happens behind the curtain, because delivering in the real time the information about the status of service quality, service availability for such demanding users like drone operators is a very challenging thing. It's very interesting. So I would like to know, for example, what are the data sources that are acquired, then processed, combined together, and finally exposed to the aviation domain, aviation ecosystem. It would be also interesting to see how the Drei operator in Austria deals with network slicing, as the network slicing standardization is not finished yet. We expect it to be finished in the middle of next year, so the commercial solutions will be available maybe at the end of the next year. For me, the network slicing is still a song of the future, but I know that there are some trials around it, maybe also the trials for the drone ecosystem in Austria. So very interesting, and I'm very, very eager to know more about all which happens behind the curtain, inside in fact, the connection between the mobile network and the RF airborne. Thank you.
Thank you, Leoslav, and maybe Thomas Neubauer, some insight.
Yes, I guess that was a question for me. So if I understood you correctly, you're with Orange in Poland, and we're talking to some of your colleagues exactly about that in very detail. It might be best to reach out directly to me so that I can provide you the long story. The short story is we're coming from a telecom background, working for the last 20 years, dealing with performance management, fault management, network configuration systems. And as such, we have a pretty good understanding of where and how, what sort of data is internally at the telecom operator available or not, and how it can be processed and has to be processed so that the limited information that is needed for aviation can be provided. Because as I mentioned, and you all know, this is about touching the ground jewels of every cellular network operation. And providing that in the time intervals required, different data sources change in different timing intervals. So we have different requirements coming from, or different possibilities coming from the telecom world. And at the same time, we have different requirements also coming from the ConOps, from the aviation side. And so making that happen, some of that data is, I would say, pseudo-static. It doesn't, the network doesn't change massively when it comes to some of the physical configuration information. However, it changes quite a lot over the course of the operation of a day, time of day, days of week, etc. As the cell loading, as an example, is a strong influencer of how the interference is composed in the airspace. And so any detailed questions, we are more than happy to deal with that offline. Otherwise, it may be stretching the discussion here a bit too much. But it is a challenge. We have been working on that for the last 5 years, working with telecom operators globally. And with Drei, we are extremely pleased to work with them for quite some time now in a detailed technical partnership to make those things happen and bring them to market. And I'll be more than happy to connect them offline with you to talk about their strategies on slicing and timelines.
Thank you very much,
thank
Thomas.
you very much.
Yes, thank you, Leoslav. Any other questions? Just please raise your hand or use your microphone. We have 8 minutes. May I ask Jonas and Maria some conclusions until we are waiting additional questions, please.
Thank you, Tanel, and thank you everybody for attending this session. There are important lessons to be learned when we do actual trials, whether they are virtual or physical trials. With the physical trials, we have the added complexity of having the physical equipment working, integrated, coverage of different radio signals, reliability of different systems. The industry is quickly developing towards higher levels of airworthiness, demanding more flexible use to the airspace. And we can see already now that there are 3 fundamental things that need to be in place in order for us to take the next step in digital aviation and an efficient urban air mobility. Those 3 steps are airworthiness, so that we can rely on a performance-based way that if we are flying over high-risk environment, we have high reliability. But we also need to accept that if we are flying over low-risk environments in low-risk airspace, we can accept lower levels of reliability from the systems. This is a mental growth journey for everyone in aviation who's been traditionally thinking that in order for it to be safe, it needs to stay in the air at all times. That's not relevant if you're flying over a lake, for instance, because if you lose the drone, you mainly lose economic value, not safety values. The other one, access to airspace, is what we are really focusing on here. How can we integrate in the airspace where most people live? A majority of the European cities are inside of controlled airspace, are inside CTR. And as a society, it is quite natural that access to that airspace needs to be possible, both for manned and for unmanned aviation. With unmanned aviation being the new kids on the block, it causes friction among our players. And it's really when we bring stakeholders together, like in these trials, have 3 air navigation service providers committing to testing, learning, discussing, enabling or stopping, that we take the next steps, because it's all people behind the business. The third one, which Thomas Neubauer and colleagues have demonstrated, is connectivity. If we want to progress with aviation, we need to make it digital. But a digital aviation relies on exchange of information, and we cannot do that without reliable means of communicating, having the ground control stations communicate to the cloud, having the aircraft stay connected to the ground control stations or the fleet management solutions. And we have in GOF been able to illustrate today in simulations that through fact-based and analytic services, we can improve the rate of success. But we have also experienced that even on the ground, we cannot always take a mobile network connectivity for granted. Sometimes we lose it, sometimes the network is degraded. In short, there are lessons to be learned for us to be able to build this ecosystem of urban air mobility to the levels that we can benefit both business and society. With those, a little bit high-level words, Maria, over to you.
Yes, thank you, Jonas, and thank you, everyone. I think maybe from the project coordinator perspective, I think we have achieved quite a lot during the wave 1 and aiming for really testing and understanding the integration. And I think that in the following days and weeks, it's really interesting to start making conclusions from the achievements and outcomes so far, and really start planning and preparing for the exciting things that we can do in wave 2 trials. Maybe this a short overview from my side.